So again, center of gravity. Sorry for in the previous video, I had to cut the video due to some reasons. So center of gravity. I'll start again. Center of gravity. So the center of gravity of an object is the point in the object that appears to the point where the weight of an object appears or is assumed to be concentrated, where an object balances, the point where an object will balance. That's what we call the center of gravity of an object, or that's the point we call the center of gravity of an object. So if, for example, you have a book and you try to balance the book, the point where you balance it, maybe you try to balance it with a finger, the point at which it balances is the center of gravity of that book. So that is all. That is what the center of gravity is. It is the weight, it is the point in the body where the weight of the object appears to be acting. The point in a body or an object where the weight of that object appears to be acting. So when you apply an opposite force at that point, it will balance that object. Okay, I hope this is understood. Now, the center of gravity of an object is the same as the center of mass of an object. The center of gravity of an object is identical. Center of gravity is identical to the center of mass of objects. Okay, so and center of mass is given by these expressions or equations. Center of mass is given by the following. No. An object or any object is a collection of tiny particles. Objects are made of tiny particles, okay? And each particle located in that object has coordinates, X, Y, Z coordinates. So we're going to be expressing the center of mass with respect to this X, Y, Z coordinates. Okay, so for position X, for example, with respect to the X coordinate, the center of mass will be M X1, M2, X2, M3, X3, and so on. Because many particles can be taken with respect to the X coordinates divided by their masses and so on. So it means in all, summation of mi xi over summation mi. So this is for with respect to X coordinates, the center of mass, with respect to the X coordinate. With respect to the Y coordinate, it's the same thing. It just changes Y1, M2, Y2, M3, Y3 plus and so on, divided by M1 plus M2 plus M3 plus and so on. So also we have a collection summation, I mean, mi yi over summation mi. So the same thing applies to the z coordinate. So if you follow this method or what we did here, it means for the z coordinate we also have summation mi zi over summation mi. Now, since x, y, and z are components of position vector r, position vector for the particles in the object, then the center of mass with respect to the position vector will now be x. Now, let me explain again. X, Y, Z are components of position vector R. A position vector, a position has X, Y, and Z coordinates. A position in space has both three components, X, Y, and Z coordinates. So this position vector R can be represented by this X, Y, and Z are components of this position vector R. So it means that the center of mass equivalent to the position vector R will now be center of mass with respect to the position vector will now be M R M1 R1 plus M2 R2 plus M3 R3 divided by M1 plus M2 plus M3 and so on and so on. And then it means just as we did for all the other ones, center of mass is summation of MI RI divided by summation MI. Okay, so this is an expression for the center of mass of an object or a particle in an object. Center of mass. Now, I have mentioned it earlier that center of gravity is identical to center of mass. So you will see how this works in questions. So we see how this works. Now, to consider gravitational torque on a body, gravitational force of gravity has the ability to create a torque on an object. Remember, a torque is a turning effect, the turning effect of a force. Force of gravity can create torque on objects. Now, to consider the gravitational torque on a body, would assume that the acceleration due to gravity is the same at every point in the body. So every particle in that body will experience the gravitational force. And then it means that the total weight of the body is the vector sum of a large number of parallel forces. Now, in short, what we're just trying to say is that for an object, every particle in that object experiences gravity, the force of gravity, and the force of gravity creates a torque effect on all the particles in that object. Now, typical particle has a mass, the typical particle has a mass of m and a weight of w. So if we're considering all the particles in an object, then we'll say they are endless, there are so many. So for the particles in an object, the mass of be mi and weight of wi, where I represents the numbers of particles present in an object. So it means weight, it's a vector quantity, is equal to mig. From secondary school, you know that weight is equal to mg. So it's the same thing. Now, still considering the position vector of the particles, then it means that the torque vector of the weight will then be, you know, I said gravity can create torque effect on particles in an object or particles in a mass. So this torque vector tau will now be equal to, sorry, let me do this well. This torque vector tau is now equal to, is not different from what you have been writing, will now be R cross this. Remember, when we did torque, we saw that tau equals R times F, right? If you have not forgotten. Now, in this equation that I have just written, you know that weight is a force. So this formula has not changed. It is still force times perpendicular distance. It's just that this time around, the force we are dealing with is the weight, because it is the weight is due to the center of it is due to the action of gravity on a mass, on an object. That's why the torque effect is going to act, is based on the weight, sorry. The torque effect is based on the weight. So the force here is as a result of the weight of the object. And we get weight by multiplying mass times gravity. So in this case, the force times the perpendicular distance here is weight times perpendicular distance. So the formula is still the same. So which then means that tau is equal to Ri times mig. Okay, so you can, this is still, it's still the same thing. Now, total torque. Now, the total torque, because we are considering particles, sum total of particles in an object. So total torque due to gravity, force of gravity on all the particles now in an object, total torque due to gravitational forces on all particles is summation tau equals position vector times m1 g, it's a vector, plus position vector 2 for each particle now one by one times m2g position vector 3 so and so on and so on. Now continuing this with this way, let's just do some little mathematical rearrangement. So we're going to have taking m and r together. If you remember, where you should be able to see where this is going. So when taking m and r together, oh, sorry, it's not a vector, it's a scalar quantity. So we shouldn't, so this instead plus m2 plus m3 and so on. So now we over and then put, now G is constant. Gravity, acceleration due to gravity is a constant. in all the cases. So we bring that out. Okay. So we'll then have summation tau. Total torque will now be equal to the total m times. Now we use I, where I represents the numbers. Okay. Times G. Okay. So we're now going to represent the total mass. Let capital letter M represent the total mass. Let it be. Let us use it as total mass. So it means that all this M1 plus M2 plus M3 and so on should be equal to, which is equal to summation Mi be equal to capital M. We want to use that. So this equation now here, this one becomes, hold on. Okay, let me clear some space. Okay, so I said, let M represent total mass, which I have put here. Now, we would multiply this equation here. That equation, sorry, this summation Mi Ri times G. Let's multiply it top and bottom, both top and bottom, by capital M. Okay? Let's multiply both top and bottom by capital M. So this becomes summation Mi Ri cross M, capital M now, please. Mg, this G, okay, divided by M here. Now remember that this M, we said, is the summation of all these little masses. Remember that this is equal to capital M. So we're going to put this here instead. So this equation becomes summation MIR times M capital MG. Now, over, instead of this M, now we're going to put this here, summation MI. Okay? Which is now our tau. Okay? Now, this expression here is the same as the expression for our center of mass for the position vector R. Okay? You can go back to that point in the video where we worked this R out, the center of mass for the position vector. So it means we'll just replace this with the position vector. So tau now equals position vector R times mg. Okay, so this is just proving that tau is equal to this. All this is proving is that, you know, mg is the same thing as width. So we are just proving that tau is equal to this times w. That's all we're proving. Okay, so tau is also equal to r times w, which we have seen earlier. Force times perpendicular distance. So let's do another example. So a uniform plank of length 6 meters and mass 90 kilogram rests on 2 knife edges. Comma, separated by a distance 1.5 meters. 1.5 meters. And equidistant from the center of the plank. A man wants to stand on the right hand end of the plank. If the plank is to remain, at rest, comma, what must be the mass of the man? Okay. So for questions like this, it's a good practice to try and draw a picture of the question so that you can see a picture of what you want to do and understand what to do. So if I just make a quick sketch. So we have a plank that is the mass of the plank is 90. So the plank is balanced on 2 knife edges. It's balanced on 2 knife edges that are equidistant from the center of the plank. So that means they are equal distance from the center of the plank. So if this is the center of the plank, then the center of the gravity of the plank should act here. And this is where the mass should act anyway. So the mass of the plank should act at this point, which is 90 kilogram, since that's the center of gravity of the plank. And the 2 knife edges are equidistant. Now the total length of the plank is 6 meters. And then there's a man that wants to stand at the edge like this. He wants to stand at the edge. So the question is now saying that what should be the mass of this man if this plank will not fall? Okay. What must this man weigh if he will be balanced on this plank? By standing here. Normally standing here, his weight acts downward. It should make this plank rotate like that. It should create a torque. Okay. So now they are saying that what mass should he weigh for this torque to not happen? For the torque to be 0. That's what the question is asking. So I hope that is clear, that we understand that. Okay, now for the man to balance, the man's mass must be such that the center of gravity will be here. For this man, to balance here, it means his mass must be that kind of mass that will make the center of gravity of this plank to shift to this point. Okay, the new center of, after he's standing, of course, the center of gravity is going to shift by the time this man stands on that plank. it must have a new center of gravity. The plank must have a new center of gravity because we are adding a mass to the mass of the plank. So the mass of the plank should rest here. I mean, the center of gravity of the plank, the new one it will have, after this man stands on it, should rest here. It should be at this point. Its mass should make the center of gravity to be at this point. Okay? Now, it means that the new center of gravity. Now, I will explain why I'm using X. Should be on this knife edge. So I'll use K to represent the knife edge. So like maybe K2. So this is K2 and this is knife edge 1. So the center of gravity should be at this point if this man is to be able to balance. Now, I'm using X because we're going to be taking the torque with respect to the X component in the X direction. Okay? We're going to be taking the torque here with respect to the X axis, the X direction, because the torque is going to allow movement in the X direction. So it's either this man is going to make this thing turn like that or like this. So from the diagram, center of gravity of the plank, center of gravity of the plank that is 0. Now, what does this mean? Here, at this point, the center of gravity acts downward. It does not create any motion. Okay? The center of the center of gravity of gravity of the plank is at the center. So it creates no movement. Here, any force acting at this center here, if the man was to stand here, it will create no rotation. It will be balanced. Okay, so that is why we're putting 0. Okay, it is at no distance. It is at the origin. Remember, I said we're taking it with respect to the X axis. Hold on, please. Let me clear this. So this is what I mean. So at this point, so here, this is our origin, 0. Okay, so the distance of the center of gravity of the plank is at 0. Okay, and then the center of gravity of the man, this man now. So I will use that, I'll write that as XM. This one is center of gravity of plank, center of gravity of the man. Now I hope you're not confused that I'm writing X as center of gravity. If you remember, I said in the center of gravity video that center of gravity is identical to or is equal to center of mass. Center of gravity is equal to center of mass, and we used we determined the center of mass for particles in the X, Y, and Z components. If you remember, center of mass, we did this, which is M1, X1, M2, X2, and so on, divided by M1 plus M2, and so on, which gives us summation m1x1 mixi, sorry, over summation mi. This x refers to the center of mass, which is equal to center of gravity. So I don't want you to be confused, okay? So the center of gravity of the man from where he is, the distance here, you can see is going to be the distance or the length of the plank divided by 2. You know, the center of gravity of the plank, the original center of gravity of the plank is, we take that as 0, the origin, okay? The origin. Now, other distances with respect to this origin, like the distance of the man, is now L over 2, which is 3 meters. Okay? Now, this knife edge 2 that we are concerned about, we'll take that one also. The center of gravity, or the location, the center of gravity of the knife edge is at 1.5 divided by 2. Okay? 1.5 divided by 2. Remember, 1.5 is the separation between the two knife edges. From here to here is 1.5. So from here to here is 1.5 divided by 2. Let's just leave this like this for easy calculation. Now, using this formula for center of gravity that I just wrote now, this x equals m1 x1 plus m2 x2 and so on. Using that, we will now say center of gravity, x center of gravity now equals to, now what are the masses involved here? The masses involved here are the mass of the plank and the mass of that man. Okay? The mass of the plank and the mass of that man. So the first one, and mass of the plank, which is, let's use that as MP, and XP plus the mass of the man times XM divided by MP plus MM. Okay? So this gives us the mass of the plank is 90. Remember that XP is 0. It's located, the center of gravity is located on the origin. That's why it is 0 for the plank. For that man, the mass of the man, which is what we want to calculate, we don't know. So M times the distance, which is 3, is XM, is 3, divided by 90 plus 3. Okay? So, X center of gravity, XCG, is now equal to 90 times 0 is 0. So we're left with 3M over, sorry, this is a mistake. It's not 90 plus 3, it's 90 plus M. We don't know the mass of the man, please. Plus M. So over 90 plus M. All right. Now we know that the center of gravity, I said this earlier, that before this man can balance, or for this system to balance, for this plank to be at rest, the mass of the man must make the new center of gravity to be here on this point. Okay, so it means the center of gravity must be equal to this, which is what I wrote earlier. Center of gravity should be equal to the center of gravity of this knife edge 2. It should be located there now. If this man should be of the right mass to make this whole thing balance. So what we are going to now do is, since we know that the location, the position of the center of gravity is equal to 3M over 90 plus M, we will now say And we know that XCG, center of gravity, should be on the knife edge 2 then. And we know that knife edge 2 is at this, this we wrote here is 1/5, 1.5 over 2. So this is this. We'll now say 3m over 90 plus m is equal to 1.5 over 2. Okay, so if we cross multiply, this will now be 6m equals 90 times 90 plus m times 1.5. If you multiply this, you have 6m equals 135 plus 1.5m. Then we have 6m minus 1.5m equals 135. This gives 4.5m equals 135. So m will now be 30 kilograms. So it means the man must weigh 30 kilograms so that the center of gravity will shift from where it is to the knife edge, the second knife edge 2. And then the system will be balanced. It will not create a torque. It will not rotate when this man is 30 kilograms. Okay, so I hope that is clear. So you can just put this down. Second, another example. We can do another example. A car magazine. So a car magazine reports that a certain sports car has 53% of its weight on the front wheels and 47% on its rear wheels. That is total normal forces on the front and rear wheels are 0.53 W and 0.47 W, respectively, where W is the car's weight. Where W is the car's weight. The distance between the axles is 2.46 meters. How far in front of the rear wheel or rear axle, how far in front of the rear axle is the car's center of gravity? Okay, so like I said, like I always say, make a sketch first. Make a sketch. So let's just draw a car. So you have that. Okay, so here, the front and the rear wheel. The distance between the two of them is 2.46 meters. Okay, so if you want to use, let's just do, instead of using cars, let's just draw a line to represent the car. Sorry, let me draw a better line. So representing that with a straight line, then these 2 points represents these two wheels. Okay, so the front wheel, rear wheel. Okay, and we know that the distance between the two of them, distance between both is 2.46. So distance between both is 2.46. And the weight, the original or the weight of the car normally should act through the center of the car and should act downwards. So we represent that with W. The total weight of the car should act downwards. Now, at this point, there will be a normal reaction from the wheels. So in the front, at the front wheel, it is 0.53% of the weight, and at the rear wheel, it is 0.7% of the weight, of the total weight. Okay. So now they are asking that the distance, how far in front of the rear axle, that is this rear wheel, is this car's center of gravity. Okay, because you can see the forces are not balanced. Okay, 53% of the weight rests on the front wheel, and 47% of the weight rests on the rear wheel. Normally, if all things were equal, the car's weight, the car's weight should rest in this at the center. The center of gravity of the car should be at the center, in the middle. But because of this unbalanced distribution of weights, then the new center of gravity will be somewhere here between the weight and between the center of gravity, between where the center of gravity should be and the rear wheel. So it's going to be somewhere here. So this is what you're asked to find. Okay? Where it will be. Now, we know, considering the conditions for equilibrium, if we consider the conditions for equilibrium, we know that the summations of forces in the x direction should be 0, and the sum of all forces in the y direction should be 0 as well. Okay? Now, there are no forces acting in the x direction because these forces are up and down. So they're acting in the y direction. Okay? Up, down. None is acting sideways. Okay? Up, the normal reaction from the rear and front wheel acting up, and the weight acting down. So that means summation of all the forces in the x direction is 0. So that first condition is satisfied. Okay. Summation of all the forces in the x direction is 0. There are no x components. There are no x components. There are no x components. So this first condition is satisfied. Now let's look at the second condition. The second condition, summation of forces in the y direction. Is it satisfied? Let's see. Upward force must be equal to downward force. So the upward forces are the 0.47% of weight and 0.53% of weight. So if we add those all together, the upward forces are 0.47 plus 0.53 W. Okay. They should be equal to the downward force. The downward force is W, the total. And they will be equal because, anyway, from percentages, you should understand this. So it means this is also satisfied because if we bring this in 0.47 W plus 0.53 W, if we bring this in, it becomes minus W equals 0. This will give us 1. If you add this together, it will give you 1 W minus W, which is 0. So it means the second condition is satisfied as well. Now, the third condition is that the sum of all torques acting about any point should be 0. The sum of all torques acting about any point should be 0. That is, there should be no, the body should not have tendency to rotate. So summation of torque should be 0. This is the third condition that we must satisfy. So let us see. Let us work that out. That is the only way we can get the answer. So I have to, let me create some space. Yep, I can clean the car. So we've seen that the first and second conditions for equilibrium are satisfied. So the last condition is what we're working on, that summation of torque is 0. So if you cannot remember the formula for torque again, you can just check. So this will now be 0.47 W times 0 multiplied by 0 times 0. I want to put the 0 in the bracket. Minus W times where the new center of gravity that we want to get. Now, what are we doing? In solving this, please, let me just explain something. We are taking moment, or we're taking the torque about this point, the rear wheel. We're taking moment about the rear wheel, or torque about the rear wheel. So I'm sure in your secondary school, you remember sum of clockwise moments must be equal to sum of anti-clockwise moments. So we need to consider which ones will be our clockwise moments and our anti-clockwise moments. So we'll take our clockwise moments as negative and our anti-clockwise moments as positive. Now, if we're taking the moment about this point, it then means that here on this point, Gogo, this R, there will be no moment. That's why it is 0.47 W times 0. Now, considering W, okay? Considering W, we do not know what the distance here is anyway. So let's take this as, since this is where we want to locate our center of gravity, then this weight, if we let's imagine that this F is not here. This force, this normal reaction here, this force here does not exist. This force or this weight W will cause this kind of rotation. It will pull this car in this direction to cause it to rotate about this point. So it's going to be W times this perpendicular distance of LG, L center of gravity, the new center of gravity that we're trying to work out. Okay? I hope you get it. Now, again, let me repeat myself. We're taking all our moments with respect to this position. We are seeing how the rotation will act with this point R as our reference. So taking this point R as our reference, this reaction of 0.4 W will not cause any rotation on this point because it is located on that point. So it's not going to cause this to rotate on this point. Nothing will happen. If all these forces are absent, nothing will happen. It will not rotate in le shele. But considering W, to by the W nìkan, this weight is pulling it down, okay, about this point. Ó máa jẹ́ kí this car to rotate like that. Kó yí about this point. It's like it's hanging here. So it's going to rotate like that. So that's why it's going to, now the distance will now be this W times the perpendicular distance. Remember, that is how to get torque. Torque is force times distance. So that's how I got that. And remember, I said we're taking clockwise movement, clockwise direction as negative and anti-clockwise as positive. Okay? Now we are done with this. Now the third one, this force. If we act as if this W is not here, let's say WU will be. This one will cause a movement in this direction, right? It's going to turn about this point. Now, this W, that is 0.53 times this distance, 2.46, and it's anti-clockwise, so it's positive. So that's why it is plus 0.53 W times 2.46. Okay? So if we work this out, here we have 0, because this is times 0, minus W LCG plus, and everything should be equal to 0 here, plus 0.53 W times 2.46 equals 0. Okay, so we now have that. If we take this over to the other side here, we'll now have 0.53 W times 2.46 is equal to W LG. Remember, this LCG is where the new center of gravity will be. That is how far in front of the rear axle is the car's center of gravity. That's now, this W can cancel out this W. So just do 0.53 times 2.46, and that will give us 1.30 meters. So it means the new center of gravity will be located 1.3 meters from the rear wheel or the rear axle. So I hope this is useful. Thank you.